Thank you. This morning, Van mentioned the idea of an ecosystem, and well, every mature technology has actually an ecosystem. And in the last 2 years, PyPy has become mature. It's now something that you can use in production, and people do use PyPy in production. And when they do that, they're actually interacting with a whole ecosystem of technologies. So this will be a rather shallow overview of each of the technology. I mostly want to point out the relations between the technologies. So, PyPy. I'm not sure it really needs introducing anymore, but, well, it's a fast, compliant, alternative implementation of the Python language, which means that it does the same things as CPython, but it does them faster. And to understand why it's faster, you need to understand RPython. So, RPython is what PyPy is written in, and what is it? It's so when I talk about RPython, it means a subset of Python that's easy to analyze statically. And then there's the RPython toolchain, which turns this RPython into C code and adds in some very interesting magic. It handles memory management for you, so that's a garbage collector, and it adds automatically a just-in-time compiler to the code you write. So, in a bit more details, the toolchain it starts with Python code. The toolchain imports it inside its own Python process. So then you get ordinary Python objects, functions, classes, whatever, and then the toolchain analyzes the bytecode of these objects, of these functions, etc. And there are a series of operations. There's a rather complicated analysis that goes on. Different compiler kind of transformations, like constant folding, discard removal, etc. And amongst these transformations, it analyzes the code to manage memory, and it also analyzes the code to create the JIT compiler. So, how does the JIT work? Well, I will not really tell you. I'll just say that it mixes the information it gathers during translation with runtime information. So what object certain function sees at runtime, and with that it generates efficient machine code for the loops you can see in high-level language. So so there are many, well, not many, but a few languages that have been implemented using RPython. There's PyPy, of course. There's also HippyVM, so that's actually my day job. HippyVM is a PHP implementation, and it's faster than standard PHP. Well, there's also a Ruby implementation called Topaz. It's a bit inactive these days, and there are several more, Prolog, Smalltalk, JavaScript. These are rather incomplete, more educational or research projects. And a bit of RPython code. Don't try to understand it. It just looks like Python code. And there's an interesting thing at the top. There's a decorator, and this decorator invokes some rather complicated meta-programming stuff. It evals templated code and all that. So you get that power, and but it's all right for the toolchain, because all this happens at import time, and the toolchain doesn't see that. It only sees the result. And once you've written a function like this, or it's from HippieVM, it implements a PHP function called strupers. And if you write a small PHP program that calls this strupers, the JIT will turn that into efficient code, even though you didn't mention the JIT at all in the previous code here. So here's what the JIT sees. All these the bold lines are calls to C function. Everything else is just one or two CPU instructions. So now I've explained the magic in PyPy. Well, I haven't really explained, but give you an idea. The rest of PyPy, the actual code of PyPy, is rather boring. It's just a big Python application, and if you try to follow it, you won't have too many problems. A bit of history. Until about 2 years ago, this was more or less the whole story about PyPy. But in the last 2 years, we've added quite a few interesting technologies to the mix, and this is what allows PyPy to be considered mature technology, to be usable in production. So there was last year there was some ARM support at the beginnings of Cffi, starting work on Numpy, and more incremental implementations. Each of those releases is faster than the previous one. And that's until 2.4, which is coming really soon. The preview is actually already online, so the real release is like this weekend probably. So the current status of running Python code, it just works. There's not much to say. If it basically if it runs with CPython, it will run with PyPy. 2.7 has been stable for quite a while. For Python 3, we have support for 3.2 since I think it's last year, and 3.3 is in progress. There are some features still missing, but I guess we have maybe half of the difference between 3.2 and 3.3. So, yeah, the speed, when we quote numbers about the speed of PyPy, it's usually an average of very different benchmarks, so it varies. But PyPy is basically always faster, and it's considered a bug if PyPy isn't faster than CPython. ARM is officially supported since 2.1, so that was last year. So the work to support ARM was mostly implementing a new backend for the JIT, because since the JIT emits machine code, it has to know, well, it basically includes an assembler, so it really needs to be the work needs to be redone for each processor architecture. All this was sponsored by the Raspberry Pi Foundation, and PyPy is now distributed in Raspbian. A few words about profiling and, well, guessing how, trying to figure out how to make PyPy code, or to make Python code faster when it runs with PyPy. The usual tools aren't they don't work well with the JIT. For when you profile either the JIT, the JITted code is a black box, or the tool disables the JIT. So that's why there's this tool which is called JIT Viewer. It's actually a little rough around the edges, and I think it needs a bit more love. But still, it's usable, and it allows you to see to see the Python code that's running, and it drills down to the bytecode and to the code that's emitted by the JIT. So you can, and even down to the assembler, if you want. And so with this, you can see precisely what JIT does, and that allows you to understand whether you're doing some things that are friendly for the JIT or not. If there were only Python code in the world, that would be it. But there isn't, and until 2 years ago, the situation was this: when you wanted to interact with C code. There is CPyExt, which is an emulation of Python's C API. It's incomplete, and it is also slow because the internal model of PyPy really doesn't match the internal model of CPython, and in particular, you can't really have pointers to PyPy objects. The objects in PyPy are moved around by the garbage collector. They can be actually virtualized away, so they completely disappear sometimes when the JIT optimizes them. So you have a mismatch here. And C-types is implemented. I think it's complete, but well, I think not many people like to use C-types, and it has the same problem that it's slow. So the third answer, and the main answer 2 years ago to people who wanted to interface with C was just don't do it. You don't need to, because PyPy is fast enough, and you don't have to go down. You don't have to replace your Python code with C. It's already optimized by PyPy. Well, that's good advice if you're thinking of writing your own C. But of course, you also may want to interface with an existing C library, and that's why we have now Cffi. So Cffi is the recommended way of interfacing with C now. I'll explain later. Let me just tell you that we also have now an API for embedding a PyPy interpreter inside a C program, and Numpy is a bit of a special case. So Cffi. It's well, it's an idea that comes from Lua. It works not only on PyPy but also on CPython, and on CPython it's well, it's sort of like C types but with a sane interface. And on PyPy, it's really fast because it meshes well with the JIT, basically. And nowadays, well, it's quite taking off. It's I think Cffi is only a year old, and there are already many packages that use Cffi. So whenever you use a Cffi package, your code becomes compatible with both CPython and PyPy. It's rather seamless. You don't have to worry about whether you're running on top of CPython or PyPy. It was the same. I'll just show you how it's done. The principle is just that you pass to describe C objects, C functions, you just pass a fragment of C code. And so on the Python side, you don't have to remember a lot of things. Here I have ICAL method. It's called cdef, open and new, and I think that's yeah. There's another one that's called verify, and that's basically it. So if you want to know more, just read the docs on Cffi. Now Numpy. So Numpy is a special case. It needs a special integration with PyPy, and therefore the core of Numpy, and by core I mean things like ND array and ufuncs. So basically the bits of Numpy that are actually implemented in C. So this is built-in module inside PyPy. It's called micro Numpy, and we also have a fork of Numpy. So that's basically a fork of the Python part of Numpy. I don't know if you know it, but in Numpy you have actually like 100,000 lines of Python, so it's not just C code. And the Python part basically works the same between Python and PyPy. So, what's the status? It's progressing a bit slowly recently. So we have about 80% of Numpy. There's, however, an important part that's missing. It's lineage. So it's lineage is the part of Numpy that interfaces with the linear algebra libraries like Atlas or BLAS. So this is still a problem for us. It's a large part of the reason why Numpy progress has been slow recently, but we are on our way to wrap this lineage bits with Cffi, and well, that should come out soon, hopefully. Well, if you want to, if you have NumPy code and you'd like to run it with PyPy, just try it. As long as you don't use lineage, chances are good that it will work. And finally, there is no Python 3 support for NumPy. It's certainly easy to fix. Well, there hasn't been much demand for it, but it would be rather easy to fix. About NumPy, I still have to add that we have NumPy support, but we don't support the rest of the ecosystem. And the approach here, well, a proposed approach would be something a bit crazy, which is to wrap a whole CPython interpreter inside PyPy and let it interact with those libraries like pandas and matplotlib and scipy. That way you would get access to all of this from inside PyPy. So yeah, that's in progress. It's experimental, so I make no promises. Now, I'll talk about the future. STM, so software transactional memory. I think it's something that will affect all parts of the PyPy ecosystem, and that will well, the goal is to allow easier parallelism for everybody, in the words of Armin Rigaud. That means that people will be able to have real parallelism without having to think about it, or without having to think about it much. So that's an ongoing research project, and and more in concrete terms, what it does is that it allows multi-threaded code to run on multiple cores inside a single interpreter. So that's basically a solution to the problem of the GIL. The GIL is well, it's an issue in the design of the Python interpreter. The thing is that the interpreter can only run a single, can basically run a single thread at once. I mean, you can have you can have multiple threads, but if they both want to actually run at the same time, the interpreter has to choose one, because you can't run two different bytecodes simultaneously. The interpreter would get into an inconsistent state. So, to avoid this, STM, what it will do, when you have two threads that try to run at the same time, it just allows them to run, but it records what each thread does. And when the thread has finished its work, you check whether there is a conflict or not. So if there is a conflict, you roll back and the thread redoes the work. But hopefully, in most cases, there won't be a conflict, and both threads will have performed their work at the same time. And you can think of a model where the transactions are quite long, and these transactions are started by just acquiring a lock at the application level. From your Python code, you try to acquire a lock, and what happens is that your thread continues running, but acquiring the lock just starts a transaction. And with this model, this acquiring and releasing of locks can be hidden by libraries who would manage thread pools, things like that. And you could have applications that are parallel without the user even being aware of it. So, the status of STM, it's still a prototype, but you can find it. The overhead is quite low. Well, 40% is not that low, except that as soon as you can run two threads at the same time, you win. So the principle sounds good, but now it needs quite a lot of work to make it, to push it to production. Yeah, there's a lot of thinking needed about the programming model when you have STM. Finally, PyPy is powered by crowdfunding. We have 3 fundraising calls that are active at the moment for Python 3, Numpy, and STM. You can also give money directly for general PyPy progress. And this month, the Python Software Foundation matches all the donations. So if for every $1 that you give to PyPy, the PSF gives another one. So that's it. if you want to know more about PyPy, the website is pypy.org. There's commercial support available, paragsoftware.com. To contact the developers, the best way is IRC. And there's a sprint on Monday if you want to know more about PyPy.
Perfect.